How's everyone doing today?
Excuse me.
So, questions before we get started?
Pardon.
Well, main objective for today is to finish up chapter 5. We'll do at least one example involving elastic potential energy, and one more concept to introduce before the chapter ends, and then that'll be the last new thing before the test. Speaking of the test, there is a test review tab on Brightspace. The tab itself has a list of everything we've covered up till now, and lower down within that tab, I have more things here that you can't see, but you'll see at test 1 practice problems. This is a practice test, updated for this year's version of the course. And if you want something to practice for the upcoming test, first of all, I do recommend doing the homeworks and quizzes, but you may also work on this practice test. And I'm going to be uploading an answer key for it, so if you want to do the whole thing and then check your answers or just look at my answer key, any option is available to you. Said answer key will show the work that I would do to get to said answers. And if you do look over this, note that I write these questions to be good practice for the different but related test questions. It's definitely not going to be identical, but the same concepts will be used. Note that I also make my practice tests longer and more difficult than the test itself, because I'd rather you make mistakes here than there. Just again, for scale, this is 11 math questions and like 5 short answer questions. The test itself is 9 questions total, so 7 math, 2 short answer. Questions, concerns, opinions, etc.? Do interrupt me with any questions related to the study guide or to any of the homeworks and quizzes you've been working on. You'll have lots of time to practice those in the coming days as well. Main thing for today is we introduced elastic potential energy last time, and if you've had lab this week, then you've utilized it at least once there. But we're going to get in a little bit more practice for it right now. To quickly review, this is the 3rd type of energy that we have covered, and it's energy that is stored in an object's current deformation, which is an elastic object current deformation. An object is elastic if it is able to deform, i.e. change shape, and then under its own power go back to normal. And the way that EPE works is when you stretch something, either outwardly or by compressing it, energy is then stored in that stretch, and once the object returns to its normal shape, that energy is released, leading to such interesting innovations as slingshots. So, for what just happened, EPE is stored in the spring. When I release that EPE, it turns into KE inside your projectile. So, 3rd form of mechanical energy. And the EPE of an object in any given moment is equal to 1/2 times its spring constant times its current change in size squared. So delta X is change in size, either by extension or by compression, because something can stretch in this way either by getting bigger or by getting smaller. Springs tend to get longer, whereas things like, balls and sports equipment that bounce tend to be compressed. And either way, that is still a deformed state using the physics definition, and stores energy in that before it is released.
So delta X is change in size of the elastic?
Correct. Specifically change in size. So if something begins at 1 meter and then I stretch it to 3 meters, What is the delta x? Very good. So it's not initial length or final length, it is the difference between the two. And then the k, the spring constant, to kind of rearrange that topmost formula. Spring constant tells you how much force is needed to stretch or compress an object by a certain distance. If something has a spring constant of 5 newtons per meter, you would have to exert 5 newtons of force on it to make it 1 meter longer, which is probably about the rating for this particular spring. It's pretty weak. And very large spring constants happen in very durable springs, like say the springs in the shocks on cars. Those would have very big spring constants, upwards of thousands of newtons per meter. Questions on these concepts before we get at least one practice question in utilizing them? All right. So, this type of example is a pretty textbook example used by physicists to demonstrate elastic potential energy. The physical scenario here, we're going to begin by launching a brick horizontally across a table at an uncoiled spring which is mounted to the wall. Think of it kind of like a bumper. It's placed there specifically to catch the object and keep it from crashing into the solid wall. Not something you see often in the real world, but physics textbooks just love sticking springs to walls for some reason. And as a result, so does web science, since it's using questions out of a textbook. And we're going to take this 1.56 kilogram object and slide it across the ground, barreling straight at this spring. So this is our before state. Now, what type of energy does this thing have before it hits the spring, before anything happens? Kinetic, very good. The box is moving. No other form is currently present because we're at a base height of 0, so there's no GPE to be concerned with. And the spring is not currently being extended or compressed at all. It's just in its natural state. It doesn't have any energy stored in it yet. Now, what about after impact? What's physically going to happen to the box and the spring on contact?
Well, the spring is going to cool.
The spring will compress, it'll be pressed inwards by some distance as the box physically collides with it and exerts force on it. And by being compressed, the spring will now have some amount of EPE stored within it. What's going to happen to the box, though, while this takes place?
The box's kinetic energy and acceleration will slow down.
It's going to lose kinetic energy, and it's going to decelerate to a stop. Again, the point of if you can kind of think of the spring here as kind of like an emergency bumper for the wall to keep things from hitting the wall. Its purpose is catch something and slow it down to bring it to a stop in such a way that it does not barrel straight into the solid brickwork. So that spring is going to physically catch the box, and as the box slows down, the spring will in that moment compress until at a certain maximum point where we're just going to pause time, the box will stop for a moment and the spring will be at maximum compression for this example. So our after state We're gonna pause time right here, right as the box comes to a complete stop. And the spring will be at a maximum compression of 15 centimeters. We're just gonna freeze time right there. At that moment, what happens to all of the box's initial kinetic energy?
It's transferred into the spring.
It's got to transfer into the spring. Initially, we have Ke, and as the box velocity drops, that's just going to vanish. Well, it doesn't vanish, it has to go somewhere, and the place it's going to go is inside the spring's compression. It's going to be stored in the spring. And since the spring has it stored up, it's saved for later, that's why if we unpause time, the energy is going to release as the box gets flung back from the spring as it returns to its normal shape. So the reason that things bounce off of springs is because the spring stores the energy and then just gives it right back in the opposite direction. And it's the same reason why, you know, a basketball will bounce when you hit it, when you throw it at the floor. It stores its own energy briefly in the split second where it pancakes against the ground. And then when it goes back to normal, that energy is released again, kinetic again, allowing it to rise up. But for right now, we're just gonna pause time right here at that point where the box is stationary and the spring is fully coiled. Questions about the before and after states compared to each other? All right, so before we can calculate how the energy is being transferred, we need to figure out how much energy is here in the first place. So how much kinetic energy will this thing have moving at that speed? Kinetic energy formula, 1/2 mv squared. You want to use that initial in motion velocity. And if memory serves, that should give us just shy of 20 joules. So that is the initial amount of energy this system had.
1997.
Someone had to do work to give the box that energy, and it just keeps it as kinetic until something stops it. And as we've already discussed, that kinetic energy is going to leave the box as the box slows down. We consult the conservation of energy. Initially, we're going to have kinetic energy, as we've described. In that moment, the spring's current EPE total will be 0 if it isn't compressed yet. But then after impact, the box's KE will change, and as the spring compresses, the spring's EPE will change. So we're going to track the changes of both types of energy from start to finish. I've already found kinetic energy initial, so I'm in favor of just dropping 19.97 right there. EPE initial for this spring. We don't know its spring constant yet, but if it isn't coiled yet, it's not going to have any. So it hasn't been compressed yet. The box has all the energy. Spring is in its base configuration. So its initial EPE is just going to be 0. Afterwards, the box's kinetic energy is going to drop as its speed drops. And if we again pause time right here where its final speed is 0, its final kinetic energy in that moment would be 0. And in that moment, the spring is compressed. Instead of its delta x being 0, its delta x is now in that moment 15 centimeters. You do not plug in 15 centimeters, you plug in 0.15 meters and then square it. So it's going to become a very tiny number. So the energy flow from start to finish, we've got initial kinetic energy because the box is moving. Meanwhile, the spring is not compressed, so it doesn't have any initial EPE. Afterwards, if we're examining this moment in time, all the KE will be gone if the box is at a standstill. Meanwhile, the spring is compressed. It'll have pretty much all of the initial kinetic energy now stored inside of itself. And its spring constant will depend on how much it compressed while absorbing that amount of energy. How you guys feel so far? No big objections? If you have any objections, I do want to know what they are. My fives look like S's today. I'm gonna just go ahead and take the two things that are zeros and make them zeros, just to demonstrate. We initially had no EPE, and after the box stops, it has no KE left. Sorry, yeah, no KE left. So, again, this is meant to demonstrate that all of the initial KE will be turning into EPE. That means 19.97 should be equal to 1/2 times K. 0.15 squared should be 0.0225 squared, if I'm remembering right. Please correct me if I'm not. 0.0112. Oh, let me check. 0.15 squared. I've got 0.0225. Okay. So, spring constant will be 19.97. I keep wanting to just say 1997 because I was alive then. Divided by 1/2 and also divided by 0.0225. And that spring constant should be
1770.
I was not alive that year. $17.75. And the units of spring constant are newtons per meter, because it again measures how much force is required to compress or extend the object. This spring, if you wanted to try to make it 1 meter longer, would take 1775 newtons of force. This is a very potent spring. Again, pretty close to car shocks. Yes?
Does that mean it goes the same for if you want to make it 1 meter shorter?
Correct.
Okay.
Now, if its base length isn't even 1 meter long, you wouldn't actually physically be able to make it 1 meter shorter. You just eventually break the thing. There is one glaring asterisk on all of this work, and it's that it stops if the spring breaks. If you enter a physical impossibility or if the spring breaks, then everything stops working. But I'm only going to give you examples where things don't break. But if it physically can't get that short, that's a non-starter. Also, if you bend it so much that it permanently warps, that's also an issue. So all of your slinkies that have kinks in them, their spring constant changes by that fact. Any questions getting at that K value or what it means? Okay. Now, spring constant does have a separate use. and we're gonna use it to figure out what force the spring is going to exert upon the box. Because the thing about springs is, due to Newton's third law, if you are currently exerting force on them to change their length, they, in that moment, are exerting a force back on you due to Newton's third law, correct? In order for me to keep this thing like this, I not only had to pull on it to get it to this shape, I have to keep pulling on it to keep it in this shape, correct? When I let go, it's just gonna snap back. And all the while I'm holding on, it's pulling on me. It wants to go back to normal. This is currently fighting my grip to try to return to normal. When you pull on a spring or push on a spring, it will fight back. And so spring constant not only serves to tell you how much force you have to exert on it to change its size, it also tells you how much force it's going to exert back when its size is changed. So, with what force will the spring be pushing back on the box when it comes to rest? The formula for that, this upper one here, force spring, that's what the S is, force spring equals spring constant times deformation. The negative just means that the force points in the opposite direction as the change in length. In the example we just did, if the spring is being pushed to the right, it's going to push back to the left because of Newton's third law. So that's all the negative sign means. It's just reverse the direction of the deformation, and that will tell you the direction the spring points in. So in this case, force spring equals negative k times delta x. We use that brand new spring constant times the change in length of 15 centimeters, and I believe that's 266.3 newtons. And so that is the force. One is the force that you'd have to push on that spring to keep it shrunk by this amount. And likewise, due to Newton's third law, that is the force it is currently pushing back with while it is compressed to this size. And that means that this is the force it is using, or will use, to push this box back. Because we've already talked about how if we unpause time, the spring's just going to push the box off of itself, spring the box away, and go back to normal, right? That's what the spring wants to do. It wants to go back to normal. It wants to release the EPE that's stored inside of it. So it's going to push on the box with that amount of force to kick the box off of the spring, give the box its energy back, and the spring will go back to its normal size. So that is what the force in the spring constant means. It's the force needed to change its length, and it's also the force it will fight back with when its length is changed to that size. All elastic objects do that, same with basketballs. In the moment where it compresses against the floor, it's going to exert force against the floor to physically bounce itself back up and return to its normal shape. Excuse me. Questions? All right. That's the last form of energy, and all forms of energy can convert evenly between the others. Springs pretty often they'll take kinetic energy and then give it back, since things have to be moving in order to compress a spring. But there are ways that EPE can turn into GPE and vice versa. Namely, if you take a spring-loaded cannon and point it straight up. EPE, KE, GPE. So any type of these energies can convert into the other types as long as you have a process that can do it. How do you guys feel? I think I asked that already. Okay. Now there's only one more thing I want to talk about. It's the last thing in chapter 5. So once we're done with this, we're going to call it for a day, and then we'll reconvene Friday to summarize and review. The very last new thing is power. And this is basically just a continuation of work from earlier. Talked about work on Friday, how work is using up energy to perform a task. Power is just the next step from that. Now, power is a term that is used fairly often in English vernacular, but kind of separately from its physics definition. And before I say its physics definition out loud, I want to refer back briefly to the physics definition of work, since the two are related. In physics, work is, again, force times displacement. To do work, you have to push on something with a force and make it move some distance. It's a good formula, it's a useful formula, it can tell you how much energy something takes, but there is a problem with it. This formula does not factor in speed or if something is supposed to be easy when a certain machine or a certain individual performs a certain task. This formula does not factor in how fast something is done, nor does it factor in if a particular entity can do that task easily or not. Say hypothetically, I am entering a pulling competition against a tractor. And I and this tractor are going to try to pull something heavy across the football field. This is not going to go well for me, but I cannot draw tractors apparently. In this hypothetical example, the tractor and I are both going to pull something across the field. It's going to take a certain amount of force to move the object, and we're both going to pull at the same distance. And so as long as I'm exerting the same force as the tractor, and I pull this thing the same distance, this formula would say that the tractor and I both accomplish the same amount of work, as long as it's the same force and the same distance. So according to this formula, I am as impressive as a tractor at pulling things. Does that sound right? I appreciate that, but no. I am not as impressive as a tractor when it comes to pulling heavy objects. We do the same amount of work, but the tractor's going to do it faster, the tractor's going to do it easier, and I'm going to be a miserable wreck after the fact. Because this formula only cares about how much energy the object being worked upon receives. It does not actually have any context for what the worker is going through. That's where power comes in. The physics definition of power is the rate at which work is performed. So the formula, the original formula that we're going to look at first, power equals work over time, the rate at which work is performed. This means that if you can do a certain amount of work quickly in a very small amount of time, that is going to increase your power output. Whereas doing the same work in more time, dividing by a bigger number, is going to drive down your power output. And that is one of the differences between me and a tractor. The tractor is going to do this job very fast. And so dividing by a smaller time, the tractor has a bigger power output. Feel good so far? All right, so rate at which work is done. Power is a new variable. It's going to be uppercase P in your formulas. And the unit for power is watts, which should be a word you've heard before. That said, raise your hand if you've only ever thought of watts as an electrical thing. Yeah, it's fair enough. It's really the only time it gets used in common English. And it's not it's not the whole picture. Hold on, I'm adding more details. The physics definition of 1 watt is 1 joule of energy used up in 1 second, or alternatively 1 joule of work performed in 1 second. So something's wattage tells you how much energy it needs every second to remain functional, and also how much energy it is able to output every second. And you know, the wattage of electrical appliances actually matches this perfectly. If you buy a 30-watt light bulb, 30 watts would be 30 joules in 1 second. That tells you how many joules that bulb needs every second to stay lit. So that is what the wattage of your devices physically means. It's joules per second to remain functional, and conversely, joules per second of work it accomplishes. So higher wattage appliances like air conditioners, refrigerators, clothes washers and dryers, they have higher wattages because they need more energy to stay on every moment, and also they do more work every second than one piddly light bulb. So the wattage of your appliances is actually the same wattage as here. It's the same unit, it tells you the same thing. There is another unit for power, though, that you have probably heard as often. And that is horsepowers. Never remember the exact conversion. 1 American horsepower is approximately 750 watts. It's approximate. It's not exactly 750. And it's just another unit of power. So when car commercials tell you the horsepowers of an engine, this is what it is telling you, the work it can do per unit time. Fun fact though, about this unit, car advertisers would love for you to think that a 200 horsepower truck is the equivalent of 200 full-grown racehorses, right? That's what they want you to think. But that's not actually what it means, because all units have to be defined from a baseline, right? In order for you to invent a new unit, you have to give a frame of reference for what that unit is equal to. 1 meter is defined as 3.3 feet and vice versa. So the definition of 1 horsepower is not actually the power output of a full-grown racehorse. It's not even the power output of, say, a draft horse, those big chunky Clydesdales that are designed to pull things. 1 horsepower, the historical baseline for this unit is the power output of 1 mine pony. The ponies that would pull mine carts through coal mines. And you had to use ponies because a full-grown horse wouldn't fit in the tunnels. So, not a full-grown horse. I wouldn't even say that, a pony is half as effective as a racehorse or a Clydesdale. And furthermore, not even just an adolescent horse, one that probably has black lung because of coal dust. So 1 horsepower is the output of a sick, overworked pony. Suck it, Ford. So keep that in mind whenever you hear car advertisers on TV. Questions? All right. One other detail on this slide before we do a very quick sample question. There's a second formula for power. I haven't addressed it yet because really it's the same thing as the first formula, and I can prove it. Power equals work over time. What's the formula for work? force times displacement. So if we write in the work formula instead of work, we get force times displacement over time. And that means this is force times displacement over time. And what is the definition of displacement over time? Velocity. So this is the same formula, just rebranded slightly. And whichever version you use just kind of depends on what information you have and what you're looking to find. Now, if I was to describe it differently, I'd say power is equal to force parallel times velocity. This would be the force you can exert while moving at speed. So I guess to compare it to a truck or a horse, they can pull very large amounts of force forward while hauling things at speed. So if you can exert a lot of force while moving very quickly, that'll be a high power output. But again, it's really the same information. You can use one version, you can figure out the other as well. Questions? All right. Let's use the new formula just a tiny bit before we break for the day to demonstrate its applications. It's moving day. Your new dorm is on the top floor of a 30-meter tall building, which is actually like 10 stories, so campus got an upgrade. So 30 meters vertical, we're only going to look at the vertical here. And your two friends are each going to carry two very heavy boxes up all these stairs. The key difference being the two boxes weigh different amounts, and your two friends will run up the stairs in different amounts of time. So friend number one is carrying 1,000 newtons, and friend number two is carrying only 500 newtons. Twos look awful today. And we are going to figure out which of these two people does more work, and then what is their respective power outputs. Now, we're only going to look at the vertical stuff here. Because if you are lifting an object, the force you're exerting while doing work would be vertical. Therefore, the parallel displacement we need to track is the vertical displacement. So even though when climbing stairs you do move forwards as well as up, we're only going to look at the up. Because that is parallel to the lifting force these two are going to have to exert. So this will just be vertical output for right now, for simplicity's sake. So person number one is lifting a 1,000 Newton box up 30 meters. So work equals force times displacement. 1,000 newtons times 30 meters. Person number one is going to do 30,000 joules of work. I can turn that into food calories real quick. That is 7 calories burned. Well, 7 calories above whatever you'd burn getting yourself up there, because you have to lift your own mass as well. Person two exerts half as much force for the same distance, so their work output will be halved at 15,000. So strictly in terms of work output, person 1 has outperformed person 2. They have accomplished a larger feat and used up more of their own energy. So person 1 wins the work competition, but they're also probably tired. But that isn't the whole story, because work does not factor in speed or ease. So now let's figure out their power ratings. Person number 1, power, we're going to use work over time. Person 1 did 30,000 joules of work in 1 minute. And since our formulas like our time to be in seconds, I'm going to put in 60 seconds instead of 1 for minutes. And so person 1's power output is going to be 500 watts. Person 2 did half as much work in half the time. So that's going to be 15,000 over 30, which is also 500. So these two individuals are equally powerful. And one of them is probably less tired. Maybe. You tend to tire out going fast. You tend to tire yourself out going fast as well, but we're not calculating that. So, speed is as important a function to power as force output is. Power cares not only about how hard you can punch, it also depends on how fast you can move. So if you can do something quickly, that is at least as good as just being able to punch hard. Questions? All right. That's pretty much it for today. That's the end of chapter 5. That's all the new information up until the test itself. I'm sorry. That is all the information that will be on the test. So I'm not going to give you any. I'm going to try not to give you anything new until the test is over. And so, looking at the list of stuff that will be on the first test. Chapter 1 was unit conversion, the intro to vectors, and our first variables. Chapter 2 was calculating those variables with formulas and various forms of motion and vector addition. Chapter 3 was vector addition, and we started talking about gravity as well. Chapter 4 was force, Newton's laws, various types of forces. Chapter 5 was work, energy, power, and somewhere along the way I gave you a few incline examples in lab. So all these concepts are summarized on test 1 and the practice test. So you look at this list, as you're studying, you should look at this list and make sure you feel comfortable with all those things, and then look over the practice test. Yes?
When will the practice test answers be posted?
I'm shooting to have that up today. What I'm going to physically do is print out the practice test, do it in red ink, and then just upload a photocopy. And again, I'll keep saying this. I always make the practice test longer and more difficult than the test itself. So, again, I say that as a comfort. If you're doing the practice test and you're feeling like, oh, this is taking forever, that's by design. Practice test is longer so that you can practice and make the mistakes before the test, which I designed to take an hour. Questions, concerns, opinions? Haiku? All right, that'll be it for today. Have lunch, let your brain digest all this information, and on Friday we'll meet again to summarize the past month and a half and make sure everyone's ready for next week. Have a nice day. Also do your homework.